So here we have a simple drop test. We'll be dropping a full mass, which is 100 grams in this case, dropping a distance of 11 centimeters onto the spring to see how much it compresses the spring. And then here we have a quarter of the mass, which is 25 grams, at a distance of 44 centimeters, 4 displacements, to drop onto the spring. This will be our 1 velocity, so full mass at 1 velocity. This will be a quarter mass at 2 velocity. So in this case, we've got as mv as momentum equation. And we have a full mass, just say it's going 10 miles an hour. So mass times velocity equals 40. So that would be as momentum. In the case of the quarter mass, or which we'll call as 1 mass, so that's going double the velocity, so we'll just say 20 miles an hour. 1 times 20 equals 20. So in this instance, the full mass has twice the momentum of the 1 mass dropping. So if momentum is a measure of energy, we should see twice as much compression. Well, not really, but just for the sake of argument, we'll say twice as much compression for the full mass at twice the momentum. So as we can see from our momentum equation, we're getting a different result, which was basically saying that the full mass at 1 velocity and the quarter mass at 2 velocity is double, the momentum. So the full mass at 1 velocity has twice as much momentum as the quarter mass at 2 velocity. But then if we consider kinetic energy and the formula, we get a different answer again. So in that case, we halve the mass and we times that by the velocity squared. Half the mass of 4 is 2. Just say the speed's 10 mile an hour, whatever. So 10 squared is 100. 2 times 100 equals 200. In the case of the quarter mass, well, say the 1 mass, we go down to a half. We have the speed at 20 miles an hour, twice the speed. 20 squared is 400. 0.5 times 400 equals 200. So in this case, kinetic energy would predict that both objects falling and onto the spring would compress the spring pretty much the same amount, because they are the same amount of energy. But if we look at MV, it would be saying that the full mass at 1 velocity has twice the momentum, and therefore it should give more compression, or twice as much compression. But ideally, if momentum was a measure of energy, we'd be looking at 1.4 the compression of the quarter mass, if we're being fair. So in this test, obviously as before, we're using a 25 gram mass, which is our 1 mass, and 4 bearings at 25 grams each, which is 100 grams. But I just wanted to show, because we're not interested in the standing weight, we're only looking at the energy. So if we put as 1 mass onto the spring, we can see that there is a very, very minimal amount of compression. Barely, it's unmeasurable for me, to be honest. So in that respect, we can just discount that. But obviously, when we put the other 3 masses on top, we do get quite a bit of compression on the spring. As you can see, it compresses the spring. And we're not interested in that. We're just interested. So basically, that I've measured, and it compresses the spring at about 3 millimeters. So the 4-mass has the advantage of compressing the spring 3 millimeters under its own weight, where the 1-mass practically doesn't compress it at all. So when we do his results, we've got to factor in the weight compression of 3 millimeters for the 100 grams, and eliminate that from the results, so we're getting a fair comparison of energy. So yeah, you can see that it's compressing. It's hard to see. But yeah, when I measured it, it's about, the uncompressed length of the spring is 75 millimeters. With the 100 grams on there, it's roughly 72 millimeters. So there's about 3 millimeters of compression for the 4-mass, and there is a bit of compression for the 1-mass, but it's just too little to measure. So I just don't think it's playing a huge role or a huge factor in this. But obviously we can see that the 4 masses together do compress the spring. So that's something we need to eliminate from the results. Right, so as we can see from the first run of the 1-mass dropping at 2 velocity, 2 being the 0 mark, obviously, we're roughly getting an average of 25 mil compression. So if MV was a measure of energy and it's twice the energy, when we drop the 4-mass at 1 velocity, we'd be looking at roughly 50 millimeters compression, plus the 3 millimeters of the, the 4-mass. So we'd be looking at a 53 millimeter compression. Obviously, twice the energy isn't going to compress the spring twice as much. So in fairness, if we say it's going to compress it 1.41 more, so we've got the 25 mil times 1.41, and that gives us 35.25 millimeters plus the 3 millimeters, so we'd be looking at 38.25 millimeters compression if MV was a measure of energy and we were being fair. Now, KE would predict the same amount of compression because they are the same energy. Obviously, we have that 3 mil factor of the heavier weight. So KE would predict 25 mil plus the 3. So we'd be looking at 28 millimeters of compression for the 4-mass at the 1 velocity. So again, we'll run the test and see what the results are. So, as we can see from the results, the full mass at one velocity compressed roughly 28 millimeters. So we did make some predictions. K predicted 28 millimeter, which would be the 25 plus the 3, which works out at 28 millimeters. MV, if we were to say, is double the energy, and it would give double the compression plus the 3 millimeters. We predicted 53 millimeters, which is 25 millimeters short of what we're actually getting. And if we were being fair, as MV being a measure of energy, and say that it would only compress a spring 1.41 times more, that would be what we predicted as being 35 plus the 3, so that would be 38.25 millimeters compression, which is still 10.25 millimeters short, so a centimetre and a bit shy of what it should be. But K perfectly predicts the energy.